In this lesson, we are going to talk about the regular matrices. We are going to define what is a regular square matrix, and we are going to calculate inverse matrices. To do this, we have to remember what is a square matrix, a matrix that has the same number of rows as columns. We have to remember how the matrix product is made, and also how the Gauss method is applied, which we use to solve linear equation systems. So, we will start by saying that if I have a matrix equation A times x is equal to c, with A a square matrix and C a standard matrix, these types of equations are resolved in a complex way, depending on the size and the shape of the matrices A, X, and C. But what happens is that if I am able to find a matrix B, which is non-null, which fulfills that B times A is equal to the identity, that would simplify the calculation of that matrix X a lot. If A is known, the C is unknown, and I want to calculate the X, because if I am able to find that B non-null, then I can multiply all that equation by B. B times A times X would be equal to B times C, since X is equal to C. Of course, as B times A is the identity times X is the X itself, the properties of the product. Then X would be exactly B times C, and with which we would have solved the problem. Of course, that always happens with B. What happens if this is B? Sorry, if this is B, it does not exist. The solution of this type of system is not simple. Well, if this B exists and also fulfills that A times B is also worth the identity, it is what is called inverse matrix A, and it will be noted by A raised to -1. It is not that it is raised to 1 power, but it is a notation. A raised to -1 means inverse matrix A. Well, in general, we define for a square matrix A, we will say that it is regular or invertible if there is another matrix of the same order, which is called inverse matrix A, and which we represent by A raised to -1. Which fulfills that A times A raised to -1 is equal to A raised to -1 times A, and is equal to the matrix unity of the same order. That is, in this case, the product would be commutative. Remember that in general, the matrix product is not commutative, but in the case of a matrix by its inverse, if it is commutative product, and also gives me the matrix unity of the same order. The matrix has 1 in the main diagonal and 0 outside the main diagonal. Well, that is called inverse matrix, and it is said that the matrix is regular. It can only be calculated, as you see, square matrix. If the matrix is not regular, that is, it does not have an inverse, then it is a singular matrix. For example, this matrix -1, 1, 1, 1, 0, -3, 2, -5, 3 is regular. Why? Well, because we are able to find this other matrix, we are going to call it directly A -1, because we know that the inverse fulfills that A times -1, and -1 times A is the identity. You can check that these products are commutative, and also gives me the matrix unity of size 3. Well, that matrix is regular. There are other matrices that are not. What properties does the inverse matrix fulfill? Well, the inverse matrix of a matrix is unique, which simplifies the cases, since we all have to obtain the same result. If I obtain an inverse matrix of a matrix, then everything is always that, and it cannot be another. It is unique. If two matrices are regular, then its product is also regular, which we can assure that if I have that A and B are invertible, then A times B will also be invertible. And also its inverse is related to the inverses of A and B. And the same thing happens the other way around. If I have two matrices whose product is invertible, then the two matrices are also the same, and also its inverses are related to each other in this way. Well, these are the properties that are fulfilled for the inverse matrices. Now, how are we going to calculate the inverse matrix of a matrix, which is what interests us? Well, we have 3 methods. We can solve a system of equations. We can apply the Gauss method, which is known for linear equation systems. Or we can apply the method of the joints. In this lesson, we are going to see these 2 methods here. And this other method, we leave it for when we define dependent systems. So, we will start. If I have a matrix A -1, 3, 1, 0, how could we calculate the inverse matrix using systems? Well, simply apply the definition of the inverse matrix. That is, I look for a matrix which has some numbers here, x, y, z, t, that I do not know. So that A times A -1 and A -1 times A is the unit matrix 2 times 2. Well, let's do those products. A times A -1 gives me, I multiply the matrix by this unknown matrix and gives me this matrix here. And this is equal to 1, 0, 0, 1. If I do the other product, a -1 times A, well, I get another expression, which also has to be equal to 1, 0, 0, 1. As you can see, if two matrices are equal, if their elements are equal 1 by 1, that is -x plus 3z has to be 1, -y plus 3z has to be 0, x has to be 0, y has to be 1, and so on with the other matrix. That builds a system of 1, 2, 3, 4 plus 4, 8 equations. If this system is inconsistent, notice that it is a linear system. If it were inconsistent, that is, if you did not have that solution, I would be saying that this A is not invertible. That is, it is singular, it does not have an inverse, and if this system has a solution, it will be a consistent dependent system. Because the solution is unique, the inverse is unique, then it will give me the value of the x, the y, the z, and the t, which forms the inverse of that matrix. Well, in this case, the system is a consistent dependent system. It has a single solution, which is x equal to 0, y equal to 1, t equal to 1/3, and z equal to 1/3. If I put each one in its position, I have the inverse matrix of the A. Well, this is the way to calculate inverse matrices using equation systems. Of course, in this case, notice that there have been 8 equations and 1 matrix, 2 by 2. As I increase the order of the matrix 3 times 3, 4 times 4, the number of equations also increases. And it is much more complex to solve, even because it may not be so simple. It depends on the starting matrix. Then, this method is not very viable to calculate inverse matrices when I'm talking about matrices of superior orders. So if for superior orders that we can use, well, the other method that we have commented, the Gauss method. What is the Gauss method? Well, if I take a square matrix regular, which I know has an inverse, well, to calculate its matrix A minus 1 inverse, what we do is to put the matrix slash and the matrix unit of size, the same as the matrix A, and we perform a series of transformations so that we interchange the matrix unit and the matrix A. We will try to get the matrix unit, and what remains on the other side will be the inverse of the starting matrix A. What kind of transformations are we going to do? For which they are valid in the Gauss method. In this case, we cannot interchange columns between them. And what we are going to do, unlike the Gauss method, is that we are going to make some under the diagonal, this one here we talked about, and also above. Well, this is what the Gauss method is to calculate inverse matrices. So for example, for the previous matrix, so that you can see that it is applied in a simple way, minus 1, 3, 1, 0, if I apply the Gauss method, I build this matrix with this bar in the middle, minus 1, 3, 1, 0, and on its side, the matrix unit of size, 2. And now I do operations. We are going to try to get a 0 here, a 0 here, a 1 here, and a 1 here. We have to interchange the identity of the matrix A. Well, let's interchange it. At row 1, I change the sign so that it has a positive 1 here. And at row 2, if I add the row 1, I get this 0 here. That would be the first option, get a 1 there and a 0 here. The next one, we are going to get a 0 here and a 1 here. Well, at row 2, divided by 3 to get a 1 here. And at row 1, I add the row 2, and so I get this 0, with which I already have the identity matrix here. As you can see, as this matrix, we already knew that it was invertible. We have calculated it before. Well, we have been able to put the identity here, and what is left is the inverse matrix. AA raised to the power of minus 1 is exactly the same as we have obtained before. Well, this method is much easier to apply, even though the order of the matrix is 3 times 3, 4 times 4, 5 times 5, etc., etc. For example, if I have a matrix 3 by 3 in this way, we are going to see if it has an inverse or not, and what it is. Well, first, what we have said, we put the matrix, and next to it, the identity matrix. And now we are going to perform operations to try to get 1s here and 0s out of that diagonal. Well, minus 1, 1, 5, 1, 1, minus 2, 0, 0, minus 3 is what it turns out to do in row 2. I add the row 1 to get a 0 here, and in row 3, I add 2 times the row 1 to get a 0 here, because I already have only 2 zeros. We continue. I change the sign to this row to get here a 1, because it is simply a change of sign, and to this, I add 3 times the second to get here a 0. Well, I already have the 0, I already have this one, I need to have 1 here and 0s up here. Well, we continue doing operations. Well, the next operation is this one. I can change the sign. Well, we have not done it yet. Simply, for example, we can go to the first row. I can subtract the third one so that, as here I subtract 0, these two will not change me, but I will get a 0 here. And the same with row 2. I subtract the row 3 twice, and I get those 2 zeros. If we continue, of course, I do the operations in the whole row, okay? If we continue, well, to row 1, I add the row 2 to get a 0 here, and to this I change the sign, which I already have here, the matrix of identity. What is left is the inverse of the A. As you can see, this matrix is regular, because we have been able to obtain its inverse. and its inverse is the one we have obtained by the Gauss method. Well, also the Gauss method allows us to determine if the matrix has an inverse or not. Well, if this can be realized, the matrix has an inverse. If it could not be realized, the matrix does not have an inverse and it would be singular. For example, in this case, this matrix A, if I put it in this way, the matrix A and the matrix of identity and perform operations, for the first one, for example, I make a 0 here, that is, I make a 0 here, row 3 minus row 1, look what I get, 1, 2, 0, 0, 1, 3, and 0, 0, 0 in this first part of here, plus the modifications of the second one. Well, notice that it is impossible to realize the type of operations in a way that I have here, 1 here, and 0 here, without modifying any of these zeros. I am not able to find any type of operation. Then it is impossible to pass the form identity in this case and something here through transformations of which we use between rows for the Gauss method. What allows us to say? Well, it allows us to say that A is a matrix. It is a single matrix that does not have an inverse. As you can see, the Gauss method allows us to calculate the inverse if it exists, or to say that it does not exist an inverse and that the matrix is singular, in case it cannot do that type of transformations. Well, with this, we have defined what is an inverse matrix of a square matrix, and we have seen how this type of matrix can be calculated. Thank you.